Hello friends, today we will discuss about the first law of thermodynamics for an open system. So there are the following assumptions. The change in potential energy is neglected. Also, the change in kinetic energy is neglected. So you can see in this figure, this is actually a PV diagram, pressure and volume diagram. The pressure is increasing vertically upward, and volume is increasing in the left to right direction. So this is actually for an open system, and this is for a closed system. So actually, in both the diagrams, you can see this is process 1 to 2. So this is actually expansion process. So here you can see expansion is taking place. Expansion is taking place in both the diagrams. So here you can see this graph is drawn for this process 1 to 2, and this is projected on the pressure line here. Okay, so here you can see for an open system, the shaded area means area covered by this process will be actually work done during this process 1 to 2. So here we can say work done during process 1 to 2 is equal to minus V dP. Okay, and this is also equivalent to the area under curve 1 to 2, means area 1 to AB1 on the pressure volume diagram, which is projected on the pressure axis. Okay, so while in case of closed system, in previous videos you have seen, this is the expansion process. During this process, volume is increasing. Okay, volume is increasing left to right. So this area covered by this curve is equivalent to the work done during this closed system, which is equal to area 1 to 1 dash 2 dash a dash b dash 1 dash. Okay, so in this case, the area 1 dash 2 dash a dash b dash 1 dash is equal to the work done 1 to 2 is equal to P dV. So here area under curve 1 dash 2 dash on PV diagram projected on volume line or volume axis, means projected on this axis, while in the open system this is projected on this vertical axis. Okay, so this is the work done in the closed system, and this is work done in the open system. So now we are talking about the work done in the open system. So there are the following conditions for the work done in the open system. So first condition, if the pressure is constant, means pressure is process is isobaric. So in this case you can see pressure is constant, then we can say delta P is equal to 0. Okay, so difference of pressure is equal to 0. There is no difference at all. So now we will apply this formula W122 is equal to minus V dP. Okay, so this formula can be applicable for this condition. So now we can say W122 is equal to integration of V dP. Here dP is equal to 0, then this term will be 0, hence work done during this process is equal to 0. Okay, so we can say for the isobaric process, work done in open system will be 0. So now we will talk about the second case. So in second case, volume is constant, means process is isochoric. So now we can say work done during this process W1 to 2 is equal to minus V dP limit 1 to 2. So this can be written as minus V P2 minus PV, sorry, P2 minus P1, or we can say W1 to 2 is equal to V P1 minus P2. So this is actually the work done for constant volume process in an open system. So now we will discuss about third condition. So this is actually the work done in open system for isothermal process. So actually isothermal process means temperature is constant throughout the process. Okay, so here we can see T is equal to constant, means delta T is equal to 0. Okay, so now we can apply this formula for the work done during this process 1 to 2. So W1 to 2 is equal to integration of minus VdP limit 1 to 2. So here we can say dt is equal to 0, means T1 is equal to T2 is equal to T3. Then we can say P1 V1 is equal to P2 V2 is equal to PV is equal to constant. So from this relation we can say V is equal to C upon P. So V is equal to C upon P. Now we will place this value of V from here to in this formula. So this formula W1 to 2 is equal to minus VdP can be written as, this is actually limit 1 to 2. Okay, so this can be written as minus C dP upon P. Okay, C is common, so you can see dP upon this P. So this is equal to minus C dP upon P, or we can say C ln P2 upon P1, or we can say C ln P1 upon P2. So this negative sign is converted into positive because we have changed P2 upon P1 to P1 upon P2. So finally we can say work done during isothermal process W1 to 2 is equal to P1 V1 ln P1 upon P2. Okay, so one more condition you can see here. So in case of isothermal process, the slope of this process 1 to 2 and 1 dash 2 dash is same. So the curve is a rectangular hyperbola when projected on pressure volume axis, and it will give the same area. So area under this curve, and under this curve on pressure line. So here we can say area 1 to AB is equivalent to area 1 dash 2 dash A dash B dash, this and this. Hence for an isothermal process we can say minus VdP, because this area is equal to minus VdP and this area is equal to P dV. Then we can say this plus this is equal to 0. Okay, or we can say PV is equal to constant. So this is the condition for the isothermal process. So now this is the case fourth, heat transfer for an adiabatic process in an open system. Okay, so in case of adiabatic process from ideal gases, we can say PV to the power gamma is equal to constant, or we can say P1 V1 gamma is equal to P2 V2 gamma is equal to constant. So here we can say from this relation V is equal to C upon P to the power 1 upon gamma. Okay, so V is equal to C upon P to the power 1 upon gamma, or we can say C to the power 1 upon gamma upon P to the power 1 upon gamma. So now we will apply this value V in the basic formula. Work done W122 is equal to minus V dP. So in this formula we will place the value of V from here. So this can be written as minus 1 upon c to the power gamma, c to the power 1 upon gamma, integration of dP upon p to the power 1 upon gamma, limit is 1 to 2. So now we can solve this relation here. So c minus c to the power 1 upon gamma is common. So in bracket we can say this is equal to p to the power minus 1 upon gamma plus 1 minus p1 to the power minus 1 upon gamma plus 1 upon minus 1 upon gamma plus 1. So solving this we can say minus c to the power 1 upon gamma in bracket p2 to the power gamma minus 1 upon gamma minus p1 to the power gamma minus 1 upon gamma upon gamma minus 1 upon gamma. So now we can take this common. So this will be reversed. So this will be actually equal to gamma upon gamma minus 1 in bracket. Now we will multiply of this c in this bracket. So this c is multiplied by multiply with this p2 and p1. So here it can be written as c to the power 1 upon gamma into p1 to the power gamma minus 1 gamma and c to the power 1 upon gamma into p to the power gamma minus 1 upon gamma. So simplifying this, so we can place the value of c from here. So c is equal to p v to the power gamma. So this value of c is placed here. So this is equal to c1, this is equal to c2. So here we can say this value here c is equal to this. So p1 v1 gamma to the power 1 upon gamma, because c to the power is gamma 1 upon gamma. So this power is here and this value is placed from here. And again we can say c to the power 1 upon gamma, c to the power 1 upon gamma. So c is equal to this value. So this is actually c, okay, to the power 1 upon gamma into this p to the power gamma minus 1 upon gamma. So now we can say p to the power p1 to the power 1 upon gamma, this one, opening this bracket, and v1 to the power gamma upon gamma, this one. So gamma upon gamma will be converted into v to the power 1 and p1 to the power gamma minus 1 upon gamma. Okay, similarly this second term. So here we can say this is equal to v1 to the power 1 and p1 to the power 1 upon gamma plus p1 to the power gamma minus 1 upon gamma. So this and this is added here. Okay, similarly for this term, so simplifying this we will get p1 to the power 1 plus gamma minus 1 upon gamma. So plus 1 is cancelled by minus 1. Then we will get v1 p1 to the power gamma upon gamma. Here you can see into v1. Similarly for the second term we can say p to the power gamma upon gamma into v2. So this will be equal to gamma upon gamma minus 1 in bracket p1 v1 minus p2 v2. So this is the work done during this adiabatic process for an open system. Similarly, in case fifth, heat transfer for polytropic process in an open system. So here only difference of this gamma. So here gamma is placed by polytropic index n. So work done during this polytropic process in an open system will be equal to n upon n minus 1 p1 v1 minus p2 v2. So this is the condition for the polytropic process. So now we will discuss about displacement work in the next video. Thanks for watching this video. All the best.